Now that you've had a chance to review how to use the periodic table, it's time to do an in-depth review of how to draw Bohr-Rutherford diagrams to represent atoms, and in this video we're going to be using chlorine as our sample element, although this procedure works with pretty much every other element. We start with the most straightforward part of representing the structure, that being representing the nucleus, and the first and easiest part of the nucleus to represent is simply taking chlorine's chemical symbol Cl and writing it in the center of our nucleus structure like this. We then remember from our review of atomic structure that protons and neutrons are the subatomic particles that are found within the nucleus, and the number of protons we can find very easily because we remember that the atomic number, in chlorine's case 17, tells us the number of protons. Now, the other thing that the atomic number tells us is also the number of electrons, so we're going to make a note of the number of electrons that chlorine has for future use in the video. The most involved process for finishing the nucleus is figuring out how many neutrons chlorine has, and that has to do with how we treat the atomic mass of chlorine. So we remember that it's physically impossible for an element to have a fractional number of protons and neutrons, meaning that this atomic mass is not usable the way that it is. We need to convert this into a natural number, meaning that we can't have 0.45 neutrons, so we need to round the atomic mass to the closest natural number. So since 35.45 is closer to 35 than it is 36, we're going to assume that chlorine has a combination of 35 protons and neutrons together. Now, if we know that chlorine has 17 protons, it's simply a matter of subtracting the atomic number from the atomic mass, which we can do with some simple arithmetic like so. So what we've done here is we've removed all of the protons from our atomic mass count, leaving only the neutrons, which shows that chlorine has 18 neutrons. And the easiest way to double check that we are correct on this is simply to add the number of protons and neutrons back together, which gives us 35, which is the atomic mass that we started with, so we know we did this correctly. Now, the most involved process of drawing a Bohr-Rutherford diagram is actually drawing the electron shells, because we need to be careful about how many electrons go in each shell and how the electrons are arranged. So if we start with the first electron shell, which is the shell that is closest to the nucleus, the first electron shell, let's just make sure that it's labeled carefully, has a maximum number of electrons of 2. And when we write electrons within each of the shells, the electrons always exist like this. So the 2 electrons that we've written in the first shell, this is what we call a lone electron pair, and this is going to be important for when we look at how atoms react with each other and exchange electrons, but again, we will see that in a future video. Now, note here that I started a count of the number of electrons that chlorine has. So in total, we should have 17. Well, we added 2 to the first electron shell, which means there should only be 15 electrons left, which brings us to the second and third electron shells, and unlike the first electron shell that can only have a maximum of 2, the second and third electron shells can hold a maximum of 8 electrons, but we add them a little bit differently. See, electrons, if we write the short form, remember that electrons have a negative charge, and two substances or two particles that have the same charge don't want to be next to each other. So two substances that are both negatively charged are going to instinctively push away from each other because like charges repel. So even though electrons exist in pairs within each of the electron shells, they do not pair unless they have no other choice. So because the maximum number of electrons in the second and third shells is 8, we're going to add 1, 2, 3, 4, and I instinctively add in a north, east, south, and west direction here. But again, as long as you start consistently and add 1 electron in each of the 4 compass directions before pairing, it doesn't really matter where you start. Now from there, we go 5, 6, 7, 8, and now our second shell is completely full of electrons. We've added another 8. So to keep total on how many electrons we still need to add, 15 minus 8 is 7. So that means that our third shell doesn't quite have the maximum of 8 electrons, it only has 7. But we add the electrons to the third shell in the same way. 1, 2, 3, 4. So we add 4 electrons before we start to pair, and then we go 5, 6, 7. And at this point, 7 minus 7 is, of course, 0. So keeping this total running tally here shows us that we have added all 17 of chlorine's electrons. And if we want to double check, we have 2 in the first shell, plus 8 in the second shell. 2 plus 8 is 10, plus 7 in the third shell, which is a total of 17, and we are done. Now, technically, especially when it comes to representing compounds, since Bohr-Rutherford diagrams take so long to draw, especially with elements that have a very large number of electrons, there is a much more simplified type of structure that we can draw that makes it easier to show how elements interact with one another, and this is what we call a Lewis structure. And Lewis structures only show 2 details of the element. Number 1 is the chemical symbol. This represents the nucleus here. No protons needed, no neutrons needed, just the chemical symbol. Now, the second detail that a Lewis structure is meant to show is only the electrons that are found in the outermost shell, which we remember is what we call the valence shell. And in this case, chlorine has 7 electrons, so we can go 1, 2, 3, 4, again, drawing 4 electrons before we start to pair, and then 5, 6, 7, and that's it for chlorine's Lewis structure. So once again, Lewis structures are a much simpler and much more shorthanded version of a Bohr-Rutherford diagram, only showing the element's chemical symbol and the electrons located within the valence shell. Now, before we move on to the structures of ions, which is covered in the next video, try the 8 practice problems below so you can see that all of the information from the periodic table that's needed to draw each of these atomic structures for each of the elements below is already given. So see if you can use the knowledge that we reviewed when drawing chlorine in order to draw the structures of the 8 elements below. And in the next video, we'll look at what happens when elements either gain electrons or lose electrons.